Imagine you are lost in a huge forest. You call your friend and say, "I moved 5 steps." Your friend will be confused. 5 steps in which direction? Forward, backward, left, or right? Now, I moved 5 steps north. Suddenly, it makes sense. You have given him both a number, or 5 steps, and a direction, which is north. This is the basic idea of a vector, a quantity that tells how much and in which direction. Vectors are everywhere. They describe how cars move, how the wind blows, how forces act, and even how artificial intelligence makes decisions. Level 0. The coordinate system. Before we start with vectors, let's talk about the coordinate system, which is kind of a map that helps us understand position and movement. Imagine you are playing a board game, and the board has squares. If someone asks, "Where is your piece?" we need a way to describe its location. This is where coordinates come in. The coordinate plane is like a giant grid with a horizontal line called the x-axis and a vertical line called the y-axis. The origin is the starting point of the coordinate plane, where the x-axis and y-axis meet. It is written as 0, 0 because both x and y have their values as 0 at this point where we first write x value and then the y value separated by a comma. Now, these two lines divide the space into 4 quadrants, or 4 regions, each with different signs for x and y. The first quadrant, located at the top right, has both x and y as positive numbers. The second quadrant, at the top left, has x having negative numbers and y as positive numbers. The third quadrant, at the bottom left, has both x and y as negative numbers. Finally, the fourth quadrant, at the bottom right, yes, you guessed it right, has x as positive and y as negative numbers. In short, if you stand at the origin and move right, your x value becomes positive. If you move left, your x value becomes negative. If you move up, your y value becomes positive. And if you move down, your y value becomes negative. For example, if a point is at 3, 4, this means we are moving 4 steps to the right, because x is 3, and 4 steps up, because y is 4. Now, if a point is at -5, 2, this means we are moving 5 steps to the left, because x is negative, and 2 steps up, because y is positive. Now we are ready to move on to level 1, which is understanding. What are vectors? A vector is simply a number with direction. Imagine an arrow. The length of the arrow tells how big the vector is, and the direction of the arrow tells which way it points. So, for this case, where the point is 3, 4, the vector will be shown like this. By the way, it is not necessary to show the vector from this origin only. It can be shown from any point in this coordinate system. Like suppose we have a point 2, -3, which is somewhere here. So this vector can be shown from this point as well. But can you tell me what will be the coordinate of this endpoint of the arrow? It's simple. Just move 3 steps to the right, which will give us x as 2 + 3 or 5, and then 4 steps up, which gives us y coordinate as -3 + 4 or 1. So the coordinate of this endpoint will be 5, 1. Now a scalar, on the other hand, is just a number without direction. For example, temperature is a scalar because it is just a number, like 20 degrees. We don't say that the temperature is 20 degrees north, right? On the other hand, velocity is a vector because it tells both speed, for example, a car moving at a speed of 50 kilometers per hour, and in the east direction. Amazing! Now we have already seen how to represent a vector using an arrow with a head and a tail, but that's not all. Vectors can be represented in a number of ways. For example, consider the same example, where a person is walking 3 steps right and 4 steps up. One way to write this vector is 3, 4 inside the parenthesis, where the first number tells movement right or left, and the second number tells movement up or down. Another way to write this vector is using unit vectors I hat or I with this thing above it, and j hat or j with this hat over it. Here, I hat represents movement in the x direction, left or right, and j hat represents movement in the y direction, up or down. This means the same vector can be written as 3i hat plus 4j hat instead of 3, 4. But we are not only restricted to 2 dimensions, we can also do the same for 3 dimensions, where we have not 2, but 3 axes, with the third one being z'd. Just imagine the corner of the walls in your house. This can be x, this as y, and this as z'd. So, in 3-dimensional space, we need 3 numbers to also include in or out movement like this. For example, a vector 3, 4, 2 inside this parenthesis means moving 3 steps right, 4 steps up, and 2 steps outside like this coming out of the 2-dimensional plane. In unit vector form, this would be 3i hat plus 4j hat plus 2k hat, where k hat represent movement in the z direction, which is in or out. The symbols I, j, and k hats are just conventions used to represent unit vectors in the x, y, and z directions, but we can use other symbols like x hat, y hat, and z hat, or simply x, y, and z to mean the same thing. These are just different ways of writing vectors, and the choice depends on the context, like physics and engineering often use I, j, and k hats, while computer graphics might just use x, y, and z. From now on, we will be using I, j, and k hats to make things easier. No matter the notation, they all describe movement in different directions in space. Now, if we want to assign a variable to this vector like we do for scalar, for example r equals 5, we take any variable and place an arrow above it, like v with an arrow, or a with an arrow, or any other variable with an arrow, to indicate it is a vector. Also, before we move to the next level, let me tell you one more thing. Assume we have a vector represented by an arrow, and if we call its head as point B and its tail as point A, then we show it with variable BA with an arrow. Also, if we call its head as point A and its tail as point B, then we show it with variable AB with an arrow. Just nice conventions. Great. Now we can move to level 2, which is simple vector operations. Assume you want to add 2 vectors A and B like this. A equals 2i hat plus 3j hat, and B equals 4i hat plus j hat. Note that instead of writing 1j hat, we simply write it j hat. Now imagine you walk 2 steps right and 3 steps up. This is one vector, which you can see is vector A, shown with this blue arrow. Then, from this point, you walk 4 steps right and 1 step up. This is vector B, shown with this red arrow. To add A and B vectors together, you combine the movements in each direction. For the rightward movement, you add the 2 steps from vector A and the 4 steps from vector B, giving you 6 steps to the right. For the upward movement, you add the 3 steps from vector A and the 1 step from vector B, giving you 4 steps upwards. So, after both movements, your total displacement is 6i hat plus 4j hat. This means you've moved 6 steps to the right and 4 steps up in total. If we represent this point by a vector with the head at origin, we get this orange color arrow. When you add 2 vectors, you can visualize their combination as forming a triangle. This orange vector represents the straight line movement from your starting point to your final position, completing the triangle formed by the 2 original vectors. This is the beauty of vector additions. Suppose we had another vector c like this, and if we added a and b with c, we get a vector which will look like this. Now, what if you want to double your movement? Imagine you have a vector 2i hat plus 3j hat, meaning you move 2 steps right and 3 steps up. If you double it, you get 4i hat plus 6j hat, meaning you now move 4 steps right and 6 steps up. This is called scaling a vector. A big number stretches a vector, and a small number shrinks it. If you multiply a vector by a negative number, the vector flips in the opposite direction. Note that the direction of the vector doesn't change when we multiply it with a scalar unless we multiply it with a negative number. Next, imagine a treasure map that tells you to walk 3 steps right and 4 steps up. Instead of walking step by step, you want to take a shortcut and go directly to the treasure. How long is that shortcut? This can be done if you traveled in a straight line in the direction of the vector instead of taking separate steps. But for that, you will have to travel this much length, which we also call the magnitude of a vector. It's easy to calculate it, right? Simply use Pythagoras' formula, or in general, the distance formula, to get this magnitude as 5. Also, this is how we represent the magnitude of a vector. Awesome! Now let us talk about unit vectors. A unit vector is a special type of vector that has a magnitude length of 1 and is used to indicate direction. Unlike regular vectors, which have both size and direction, a unit vector only cares about direction. Think of it as a pure directional guide, like a compass pointing north, without telling you how far to go. Mathematically, if you have any vector A, you can find its unit vector by dividing it by its magnitude or length. This process keeps the direction the same, but ensures the length is exactly 1. The formula for a unit vector u in the same direction as vector A is u equals A divided by the magnitude of A. Now consider this example where A is 3i hat plus 4j hat. We know that magnitude of A will be 5, so we say that the unit vector of A, or u, with an arrow will be equal to 3i hat plus 4j hat over 5. In the problems we have been solving, you have already seen unit vectors in action. The symbols I hat, j hat, and k hat represent unit vectors along the x, y, and z axes, respectively. These unit vectors help break down any vector into smaller, easy-to-handle pieces, making vector calculations much more intuitive. Now is the time to jump to the next level, or level 3, dot products. Suppose we have 2 vectors, A and B. In 2 dimensions, vector A is written as A, 1i hat plus A, 2j hat, and vector B is written as B, 1i hat plus B, 2j hat. To find their dot product, we multiply the I hat components together, then multiply the j hat components together, and finally add both results. This gives us A dot B equals A, 1 times B1 plus A, 2 times B, 2. If we extend this to 3 dimensions by including a k hat component, the formula includes one more term for the k hat direction. In this case, the vectors become A, 1i hat plus A, 2j hat plus A, 3k hat, and B, 1i hat plus B, 2j hat plus B, 3k hat. The dot product follows the same pattern. We multiply the I hat components, the j hat components, and the k hat components, then add all 3 results together. This formula is useful for measuring alignment between any 2 vectors, whether in 2 or 3 dimensions. Note that the dot product of perpendicular vectors is 0, and the dot product of parallel vectors is the product of their magnitudes. Now, the dot product between 2 vectors can be visualized as the projection of one vector onto the other. Imagine shining a light on one vector, casting its shadow onto the other vector. The length of this shadow represents the magnitude of the projection, which is directly related to the dot product. If the vectors point in the same direction, the projection is long, and the dot product is large. If they are perpendicular, there's no shadow, and the dot product is 0. If they point in opposite directions, the shadow points backward, and the dot product is negative. The dot product has several important properties that help us understand how vectors interact. The first property is commutativity, which means that the order of multiplication does not matter. If we take two vectors A and B, then A dot B is always the same as B dot A. This is similar to regular multiplication, where 3 times 4 is the same as 4 times 3. The second property is distributivity. Mathematically, A dot B plus C is the same as A dot B plus A dot C. The third property is the dot product of a vector with itself. If we take a vector A and compute A dot A, this result is the length of A squared, which is useful in many calculations, such as finding distances. The fourth property is that if two vectors are perpendicular, meaning they form a right angle, then their dot product is always 0. Imagine you're pushing a heavy box across the floor. The goal is to move it forward, but what if you're not pushing perfectly straight? If you push directly forward, all of your force goes into moving the box. If you push at an angle, only part of your force helps move the box forward, the rest just presses down on it or wastes energy. If you push straight down, the box doesn't move at all. This is exactly what the dot product tells us. It measures how much of your force actually contributes to movement in the intended direction. Let's say you are pushing a box with a force of 3I hat plus 4J hat, meaning 3 Newton force to the right and 4 Newton upward. The box moves 5I hat, meaning 5 meters to the right. We calculate the work done using the dot product of the force vector and the displacement vector, which we represent like this. Multiply the I hat components, 3 times 5, which is 15. Then multiply the J hat components, 4 times 0, which is 0. Now add the results, 15 plus 0, which gives 15. So, the work done is 15 joules. So we see that only 3 Newton force in the x direction was useful in calculating the work done on the box to move it horizontally. The dot product is also useful for finding the angle between two vectors. Suppose we have two vectors, A and B, like this. We know that their dot product is found by multiplying the I hat components and the J hat components separately, and then adding them together like this. At the same time, the dot product can also be written as the length or the magnitude of A times the length or magnitude of B times the cosine of the angle between them, say theta. Magnitude of A equals square root of A, 1 squared, plus A, 2 squared, and the magnitude of B equals square root of B, 1 squared, plus B, 2 squared. By rearranging the formula, we can find the cosine of the angle theta as A dot B divided by magnitude of A times magnitude of B, or this. Once we get the cosine value, we can use a calculator to find the actual angle. Let me know in the comments what will be the angle between these two vectors. Now we will level up our gear and move to level 4, which is cross product between two vectors. The cross product of two vectors A cross B results in another vector that is perpendicular to both of the original vectors. The magnitude or length of this new vector is equal to the area of the parallelogram formed by the two original vectors, which will be the magnitude of A times the length or magnitude of B times the sine of the angle between them. Say, theta is the angle between them. The direction of the resulting vector is determined by the right-hand rule. If you curl the fingers of your right hand from the first vector to the second vector, your thumb points in the direction of the cross product. When you tighten a bolt with a wrench, you're applying torque, which is a kind of rotational force. Torque is calculated using the cross product. The force you apply is a vector, and the distance from the bolt to where you apply the force, the lever arm, is also a vector. The torque is perpendicular to both of these, causing the bolt to rotate. Torque is given as a lever arm vector cross-force vector. The direction of the torque determines the direction of rotation. So if force is applied like this, in this direction, and the lever arm is like this, or this vector, then using the right-hand rule, the direction of the torque will be inward, and thus the bolt will rotate like this. Now keep this thing in mind to make your calculations easier. Write I, J, and K like this. Now I cross J is this K, then move again clockwise to get J cross K as I, and finally K cross I as J. Also note that the cross product with itself is 0, which means this. The cross product is anti-commutative, which means that swapping the order of the vectors changes the sign of the result. So if you have two vectors A and B, the cross product follows this rule A cross B equals minus of B cross A. So for example, if you take K cross J, it will become minus I. You got the point. To find the cross product of two vectors, A and B, we need to take each component of A and cross it with the corresponding components of B. Let's say A is 2I hat plus 3J hat minus K hat, and B is I hat plus 2J hat minus 2K hat. Cross product is given by this formula where A1, A2, and A3 are the components of vector A, and B1, B2, and B3 are the components of vector B. In our case, A1, A2, and A3 are these, and B1, B2, and B3 are these. Let's plug these values into the formula to get A cross B as minus 4I hat plus 3J hat plus K hat, and this vector will be perpendicular to both A and B vectors. Great! This has already become a very long video, and thus I will stop it here. Now if I get 10,000 likes in this video, then I will make a part 2 of it, which will cover all these brilliant topics. That will definitely blow your mind. Also, if you like it, please don't forget to share this video with your friends and support this channel by joining our community and becoming a member. So good!